Before I actually go into the topic, this talk has a story, uh, and it started a few years back when I realized that maybe I should start learning about functional programming. My formation has been first as a C++ developer, then I moved to C#, Java. I started supporting developers, pairing with them, supporting them with technical practices, and often also in C++. But I am not doing full-time C++ development. I'm helping teams and people whenever they need support with practices, refactoring, unit testing, test-driven development, things like this. And last year at CPP Europe, I did a talk that is online, that you can see, on functional programming. It was different from this one, of course. I'm not doing the same one. And that's more focused on kind of the building blocks and how to use them. And later, I got a book deal because of those slides. So Peck Publishing saw my slides, and then they said, oh, you seem to know what functional programming is about. We need you to write a book. And I said, okay, fine. That's interesting. But the thing is, by writing this book, I'm now kind of in the middle. I realized that I had to learn much more and to explore much more topics and so on. And so that's why today we are here with, let's say, an updated view on how functional programming can work in C++. And my approach to this has been very practical. You find a lot of articles on functional programming which start from the mathematics. They tell you about lambda calculus and category theory. And that's really nice for people who have time to sit down and read all that and understand the math behind. I encourage you to do so if you are so inclined. But the reality for many developers is we don't have the time, we don't have the patience to actually go into these details. So what I want to do is rather look into how we can use these ideas in our real life, in our production code. How can we improve our code with functional programming concepts? So that's why it's not purist. I will not talk about mathematical concepts. Actually, some of the things that I will say are probably controversial. I will not touch on performance. That's just because of time limit. It's a very complex topic, and we can certainly discuss it later on. But what I'd like you, if possible, if you can take one technique from here, from this talk, and apply it later, that would be a good result. So let's start. There are two core ideas about functional programming. There's probably more, but once you start distilling it, functional programming comes to two core ideas. First core idea is immutability, and the other one is that functions are data. And let's look at why these are interesting. So first of all, I learned about immutability coming from the perspective of clean code. There's one fundamental problem in programming, which is we need to read a static representation and in our brains run it so that we figure out how it will work as a behavior in a program. This is something that I often do, that I do most of the time when I'm writing code. So then if we add more obstacles to this type of translation, it becomes less effective and more challenging. You get tired earlier, and so on. So if I'm looking at a function that allows me to mutate the parameters, it has a lot of possible implementations. So of course, there's the most natural one, the one that I would expect, but I've seen code that does other things. right? Or this one. And in fact, if you look at the add function, and if you just take the basic pass by value, pass by reference, pass by pointer, you get a number of combinations for this function, right? And this becomes a bit difficult to grasp. On the other thing, if we are talking about immutable code, there's one way of writing this type of function. And often programmers fear the idea of reducing their options, but I think reducing our options is mandatory. It's actually extremely useful. Because if you are reading this signature, you know what to expect. Your translation is much faster, much easier. You know how to call this function, you know what it will do, no surprises. When there's no surprise, I'm a happy programmer. So of course, then you have this type of implementation. So just briefly about immutability, there are much more ideas around immutability, but one brief idea is just that it supports our translation effort. It gives us no surprises. It allows us to focus on actually using the functions that we have in our code instead of trying to figure out how they work, which is probably what everybody wants. The second core idea is that functions are data. This is, of course, is not a new idea in C++, right? We had function pointers. Well, I remember using function pointers 10 years ago. We have functors. I think I used functors 10 years ago. It's not a new idea. But because of the functional programming construct, it leads us to another types of constructs. So I want to insist a lot on the syntax. I assume you all know kind of how lambdas work in C++. And if you don't, we can chat later. But basically, this is a lambda variable. You can call it as a function. The important thing is, unlike in pure functional programming languages, lambdas can mutate. So you need to pay attention to this as well. This is a case where if you pass the parameter by reference, you can mutate it and it will actually change. So then you need to be careful when you use lambdas to also combine it with immutability. It doesn't come out of the box. It needs to be written into the function. Another property that I like, and that's probably something controversial, is the type inference. If I want to write a function that has auto in its signature, the compiler doesn't let me. If I want to write a lambda that has this, the compiler allows me to do so. Now, I know I've been in the school of strong typing, and I like the idea of strong typing and what strong typing can do for us and how it can support correctness in our code. Unfortunately, what I noticed is that in practice, strong typing is often binding my hands. And I'd rather have some kind of type inference that works most of the times. That's a preference. So again, if you talk to many functional programmers, they will tell you strong typing is very important, absolutely mandatory. I disagree. I prefer weaker typing. Of course, this construct has one problem. The problem is if you call this lambda with values that don't have operator plus defined, you will get a strange error. The way I deal with that is by working in small steps. So I compile a lot, I run tests a lot. So then I know immediately what is wrong. But if you get 100 errors like this, yeah, it's not that nice. And one last property of lambdas, you can capture values, and this will be important for our next examples. What it means to capture values, in this case I define first as a value It's 5, right? And the equal sign in the square brackets means that it's captured by copying it. And you can see I can use it inside the lambda, right? But this is just, kind of the fundamental block. Now, the more interesting thing is that functions are data. Because functions are data and we can do operations on data, we can also do operations on functions. That's the more interesting part. So what kind of operations are we talking about? There are 4 types of operations that are usually discussed when we talk about functions in functional programming: partial application, functional composition, currying, and higher-level functions. I will quickly go through the ideas, and then I will show you some code that will support these ideas. So first, what is a partial application? So it's an operation on functions. What this means is I'm passing a function in, I'm getting a function out. Right? In this case, I'm passing a function that has n parameters. I'm binding one parameter to a value. I obtain a function that has n minus 1 parameters. So the syntax in C++ uses the bind function. All examples are in C++ 17, by the way. So that might be a problem for some code bases. I'm using bind here, and I bind a special value there to be 10. So that thing is equivalent with writing a completely new function that divides 10 by a second value. And I will come back to this example in the code because the bind syntax is a bit confusing. Second operation that we discussed about is functional composition. You may know this from math. It's basically when you have two functions f and g, you call f of g of something, you obtain a new function. This is what it is. Unfortunately, there's no operator that does this in C++ yet. Fortunately, it's fairly easy to write one. And that's how you can write it. It uses template type names and captures f and g as parameters, returns you a new function that is f of g of whatever parameter you pass in. This is already, let's say, a higher-level function. You see we have a function that returns a function. It's turtles all the way down. That's the way of functional programming. And if we want to use it in an example, let's say we want to increment things twice. Of course, we don't want to call increment of increment because that's boring. So what we'll do is compose increment with increment, and then we can actually call this function. Currying is another thing. Currying is often misunderstood and is confused with partial application because it has a very similar, they are very strongly related. What currying means is the other way around of composition. So we have a function with n parameters. We decompose it in n functions that take only one parameter. Again, there is no operator in C++ that allows us. This is how you would write it. So capture the first parameter or bind it is the same thing, and return, the result. The interesting part is that in a pure functional language, you would do this by default. So if you call a function that takes two parameters with just one value, it will return you a function that gets the other missing parameters. Now, maybe an interesting fact is you may have heard about the Haskell programming language, and we just talked about Curry. Both things, this is very rare in software development, both these names come from one person, Haskell Curry. He had so many contributions to functional programming that they honored him in multiple ways. Sorry? Okay. Ah, nice. I didn't know that, but it's a nice piece of history. Okay. And probably the most boring thing, because we've been using this for years, is we can pass functions as parameters. Because functions are data, you can pass them as parameters, no problem. We've done this for years. The only thing that's different now is probably that we can also pass the lambda thing. And I won't go into the list of high-level functions, but there are many of them in STL. You can find them in, I think, functional or numeric headers. For some reason, they are separate. Right, let's see some code. I'll need to switch microphones quickly, so I'll be right back. Okay. Okay. Right. Can you hear me now? Yes, no? Okay. Perfect. I'll try to, I'm not used with this type of microphone, but let's see. What do we have here? We have a few examples. We can run them. Can you see the code? Fine? Yeah, okay. There are actually more examples here, but you'll see that we are running these and also running the tests, just to be simple. So what we have here is what we've discussed. First, it's a partial application for lambdas. And here we have bind. So I'm using here a function add. I'm binding both values. By the way, I'm using 42 here for two reasons. One is the answer to life universe. And the other reason is it's my age now. So I still expect to get the answer to all these things. Exactly. So what you see here is that I'm binding the both of the values to add, and it's 5 and 37, right? So when I add them, it's 42. That's the easiest example. Now, where it comes a bit weird is if you want to bind only one of the arguments, because bind uses these argument placement things. And what was very confusing for me when I tried them is it took me a while to realize that this actually is the number represents the number of the argument from the resulting function. So when I say _1, it's actually the first parameter of the resulting lambda. It's a bit confusing. So actually this is equivalent with having 10 over the second argument, because this second argument is actually first argument in the resulting lambda, which is _1. Okay. And so what we can do is to bind either the first argument or the second, and you can see the difference in results here. First we have 10 by 2 is 5. Here we have 100 by 10, which is 10. Let's look at the functional composition. So as we said, we have a function increment. We want to do increment twice. This is how we would usually write it in standard, let's say, the way we are used. But if we use this nice templated function for composition, it will return us a new function. So what we have here is, if I'm doing increment, I want increment twice. I can run compose of increment and increment, and I can actually check it works. Right. You can find this function, and if you try a bit, it's relatively easy to write. Let's look at currying. So currying is something like this. If we have add here, we have curried add. It would be nice if I'm using add here instead. And as you can see, I need to capture it. I don't know why first. First is not used, yes. I need to do this. And you can probably make this more general by creating more types of currying functions, because so add here can be passed as a parameter. I could probably generate the curried version of any function with 2 parameters quite easy. But if I want to do for 3 parameters, 4 parameters, and so on, the only way is to write more implementations. I couldn't find any other way. So it would be nice to have a kind of standard currying function. How do I call it? Well, I can call it like this, right? It takes 2 calls because it's actually 2 functions now. Why is this interesting? Well, let's look at combining currying and compose, for example. What happens if I have increment, but I want to, so I have a divide function that is curried. I have an increment function, and now what I want to do is to compose them. But just to compose on one of the parameters, because increment just takes 1 parameter, right? So there are 2 options. I can divide the incremented value with the second, or I can divide the first thing with the second value incremented. And the way I do that is just by using compose once with the curry divide thing. So I'm composing the 2 functions. What happens? 41 is incremented by 1, divided by 2, I get 21. The other way is a bit more weird, because I need to pass in a value. So remember, curry divide the first will actually give me a function. So I can compose this function with increment, which is equivalent, again, 1 passes in as the second parameter. It is incremented because it goes through the composition. And then 42 divided by 2 gives me 21. And that's how it works. And you see, it's a completely different way of thinking about functions, because you can take the function, break it apart, getting it back together, recombining it in various ways, and that's how you get more interesting behavior out of very small, precise functions. And the last example, which is, again, it's not very interesting because we've been doing this for a long time, just calling sort. Right. That works. Right. Let's go back to the presentation. Okay. Oh. Sorry for that. No? No. Complicated to change things. In the meantime, if you have any questions. Yes. So you see, that's where my knowledge kind of stops. So if we can find any solution for this, I'd be happy to explore it. But okay. Okay. Right. So I wanted to show you the operations you can do on functions. Now let's look at applying this. I like to use small problems first to explore this kind of completely mind-bending ideas because it's fairly difficult to test out these ideas without having something that's a problem that's relatively easy to understand. If I have a problem that's fairly difficult, I'm doing it at work, it will be very hard to actually learn this. So one problem that I had a lot of success with for myself and for others who are trying to explore this is what I call the tic-tac-toe result. Basically what this says is we have a tic-tac-toe board which can be in any various of combinations. So it's a 3x3 board with X and O's on it. It can be empty, it can be full. We have no idea. We just have to determine what the result of the game is. Right? It's very simple. But the more important thing is how you approach this problem. And how I approach these types of problems is by giving examples of inputs, giving examples of outputs, writing them down and trying to figure out patterns and how to order them so that I can start from simple implementation to more and more complex implementation. And what comes different when I'm talking about functional programming is that I'm trying to find a chain of transformations to apply on the input data so that I get to the output. One trick that I learned from business analysts that are really professional in their job is that it's usually easier to start from the output because the output tends to be better defined. You kind of know what you want to achieve. Usually that's what you can get from business people or people who are requesting stuff from you. It's harder to get from them what the inputs are. So these are all the possible outputs, and we'll just focus on one of them, X1, for now. I wrote some representations of the board, so this is how I see it. And then it turns out that if I'm doing this analysis, When does X win? Well, if any line is filled with X, or any column is filled with X, or the main diagonal is filled with X, or the secondary diagonal is filled with X, this gives me the win condition. Sometimes you can get to this just by looking at the problem, but oftentimes I prefer to just write it down and figure out the exact algorithm. So if I'm thinking in functions, I'm thinking in this is my input data, that's my output data, how I can get from input to output through a series of transformations. And the first transformation, so in this case, how would I write this kind of pseudocode functional thing? I have the board, I need to turn it into a collection that contains all lines, all columns, all diagonals. Look through every element in this collection. If any of them is filled with X, the next one. That is, and of course, again, I'm not talking performance here, right? That's separate. What does filled with X mean? If I'm given any line, column, or diagonal, or tokens on L equals X. And if I write this code, I'm getting a number of functions, and we'll quickly jump into the code in a moment. And then I can start seeing patterns between these functions. I have functions that take similar parameters. What can I do? Partial application, or it turns out I can use classes for this. If I have same structure inside the function, we can use higher level functions. So functions that receive functions or functions that return functions. If I have chained calls, I can use functional composition. So that kind of separates the core domain, the functions that are actually doing something important and interesting, from the other things that are just connecting tissue, are just connecting things together so that they work. And again, let's look at the code. Okay, I'll switch microphones again. Okay, so I'm going to start at the end. I have a test case here that says, this is my board, and let's just check the text wins here. I had more test cases, but this is just a simplified version just to show you the principles. So, interestingly enough, I can write this almost exactly as I wrote it in text. It says any of collection, all lines, columns, and diagonals, line filled with X. Now what I've done, and I'll show you at the end, I did an implementation that wraps any, all from STL to work on the full collection and not, because otherwise I have to pass in dot begin, dot end, and it's getting a bit annoying. So let's look at what's happening in all lines, columns, and diagonals. Interestingly enough, it just concatenates all lines with all columns with all diagonals. It's just technical detail. I didn't know how to concatenate them. I had to write another function. So how is all lines implemented? And this is where it gets a bit interesting. I realized at some point that you can also, it's slightly more difficult to see this, but this is actually a transformation, because what I want is I want to take the board and I want to take every line. But what are we transforming? What are we transforming is actually the initial indexes, because I have a range from 0 to 2, basically. And usually in other languages, I can do it differently. Here I had to do a to-range of board. I implemented a function that takes the board, which is basically a vector. It doesn't really matter. It gives me that range. I go through 0, 1, and 2, and I return a line. What is a line? It's a board of line index. Similarly, the column, let's look at all columns. All columns takes a range, goes here, calls column. What is a column doing? Is just doing the reverse of the line, right? So it takes a column index, but then it needs to go on every line and take the element of that column index. And then how do I do main diagonal, secondary diagonal? Well, there's a mathematical property there. The main diagonal has the same indices. Secondary diagonal, sum of indices is size with a 1 difference, right? Sorry. Okay. So that's basically how it works. And then we have some of the connecting tissue, which is these things transform all. Again, I don't want to write every time source.begin, source.end. I just wrap them. I have all of, any of, and so on. And this all put together gives me a program that works for the condition of X winning. Now, you may have noticed some of the things here. There are some duplications. Column looks very similar with diagonal, looks very similar with main diagonal, looks very similar with line. There's a similarity in the body of the function, in the structure. What can we do? Extract a higher level function. If we want to implement this, so let's look at xwins. Xwins calls line fields with X. We have an X here, right? You can imagine if we are implementing this for O, we'll have another function, same body, O comes there. What we said we can do, we can bind the parameter, have a general function, bind the parameter. So let's look how that works. It turns out that it's even more higher level. So I extracted here more functions, but in principle, what we have is a kind of token wins, passing an X and an O. We have a new function without doing anything. It's just a functional operation. What happened with our line? Our line, interesting enough, I realized that the only thing that I'm doing is basically projecting some coordinates. So I have the board. What I need is to generate the sets of coordinates that I'm using for main diagonal, secondary diagonal, line, column, and so on. And then just have a high-level function that takes the board, takes the coordinates, returns the projected result. So everything that is line, column, secondary diagonal, main diagonal, they are just projections now. And the interesting part to all of this is I can change the size of the board. I don't have to do anything. I can do a 5 by 5 board, I can do a 50 by 50 board. Again, if we ignore performance, which I know may be hard for some people, nothing changes. The code is exactly the same. If I want to add another player, Y. I bind to player Y. It will still work, of course, maybe with some slight modifications. So there's this power that comes from separating into smaller functions and then combining them to obtain more advanced behavior. Right. And I don't know how long I still have. There's one thing that I'm exploring now, which is related to this. We have this problem of legacy code. We have code that's been written for many, many years. We don't understand it anymore. And I like working with this type of code. I like changing it. But it's always been a very difficult journey because you need to learn a lot of things. You need to learn about how to write unit tests on existing code. You need to learn how to refactor it, how to do proper software design, and so on. And often you need to use some very weird techniques to get from your code to code under test to refactored code. So what I'm now exploring is another method of refactoring such code, which heavily uses immutability and the techniques that we've been discussing. Because I realized at some point that we can write any program as some kind of input, some kind of state, and the core that is immutable. And the fun part about this property is that you can apply it on a whole program level, on a class level, on a function level. It's quite fractal. You can zoom in, zoom out. So you can take a piece of the code, separate what's immutable from what's not immutable, and go from there. And so what I'm trying to do, and it's still a work in progress, but I'm sharing this in hope that some of you might have input on this. I'm using the compiler so I extract a piece of code, try to make it const. It will tell me, you cannot do this because of X, Y, Z variables. Extract them as parameters or as functions. Try it again and again and again until I get an immutable function. And what I will obtain is an immutable function, but that probably has a lot of parameters because I need to pass in a lot of the data that it's been using, a lot of the state that it's been changing. But then I can decompose this into smaller lambda functions. And for all the other steps, I have some mechanical ways of doing this, but for this one, I'm still trying to figure it out. And at the end, I can look at the functions and remove duplication from them. How? Grouping them into classes if they use the same parameters. What I'm getting as a result is a small class that is immutable. Or classes that just receive data, return data. And it's more like a service class. So this is interesting because you end up with a functional object-oriented approach. And my hypothesis is that, which is still unconfirmed, is that I can do this through mechanical steps without necessarily using tests, or once I go to the immutable function, it's much easier to write tests for immutable functions. And there, I can use property-based testing or other advanced techniques to support me in my effort. So that's it. Immutability and functions as data. Simplify programming. Try them out on your code. You can, again, these links are clickable. You can find them in slides. There are previous slide decks that I used around these similar concepts. We have some workshops on C++ if you are interested in them. So if you just visit mosaicworks.com, you'll find them there. And my book is available for pre-order. If you have any questions, I'd be happy to answer. Thank you.
So maybe we have 1 or 2 minutes for one question. Then Alex will be around.
A common technique in refactoring is, or class construction, is that essentially the constructor of the class takes a number of parameters. Then what you have is a number of static member functions in which one operates on these parameters, combines them, etc., assigns the results of that in the initializer list of the class so that the class members can actually be const. And then you don't need any getters or setters at all. And you have essentially you have essentially a data flow model in which you've got data transformations occurring in which the classes capture that data transformations. Have you considered that at all in your refactoring?
I think this is one of the patterns that I have seen less often. So what you are saying is that the data is actually modified inside the constructor. Am I getting this right?
You've got the combination of the different. Imagine I want to do an add, then my add class might have a constructor that takes 2 parameters, 2 ints, and then the result const int result, and in the initializer list, result open parentheses 1 plus 2, or first parameter, second parameter. And I might have more complex things like, say, for example, look them up in a database or do an HTTP query. So this may be a static member function which performs this and then returns the result because, of course, it's much too long to put in the actual parentheses in the initializer list.
Yeah. Well, so what I like is usually to pass in dependencies. And what we talked about here, actually passing in functions is another way of dependency injection. It's probably the simplest or more down to the basics way of doing dependency injection. So usually that's what I prefer. I'd rather pass in a function that can read data or another object that can read data. Another interesting thing with this is when you think about methods in classes, they are actually, if you get into account all the member variables and you pass them as parameters, they are actually bound at the constructor level. So that's equivalent with partial application of the data members that you receive in the constructor. So that's why I think these two are kind of interchangeable. I will look at my resulting lambdas and say, oh, this kind of look like they fit together in a class because they kind of use the same things. And they are more cohesive. I don't know if I'm making sense, but yeah, okay. Thank you.